Hi everyone, today we are comparing the O2 molecule with the O2 plus, O2 minus, O2 plus 2, O2 minus 2 in terms of stability, bond length, bond order, bond energy and magnetic nature. It is a very important question, but majority of the students a little bit confused every time. To avoid that confusion, I made a video with a small techniques by using the concept. For learning, for getting the clarity regarding this concept, student must know the terminology and concept and relation between different parameters. What are the terminology we required here? The terminology required here is HOMO, LUMO. What is HOMO and what is LUMO? High energy occupied molecular orbital, lower energy unoccupied molecular orbital, and what is called concept? Molecular orbital theory. Student must have the knowledge of the molecular orbital theory. If the student have no such a knowledge regarding molecular orbital theory, this video is not fruitful to you. And relation between different parameters. Here parameters is stability, bond length, bond energy, bond order and magnetic nature. Of course, I will supply some information regarding HOMO, LUMO and molecular orbital theory and relation between different parameters. First we will discuss about the different relation between different parameters. In this video we are going to make relation between stability, bond length, bond energy, bond order and magnetic nature. First of all, what is called bond order? What is called bond energy? Bond order, first I am taking the bond order. The average number of bonds between two atoms in a given molecule is called bond order. If bond order 1 means only one bond exists between the two atoms. Bond order 2 means between those two atoms two bonds are there. Bond order 3, that means 3 bonds are there, very simple. If you take the O2 molecule, 2 bonds are there. If you take the N2 molecule, 3 bonds are there. So here bond order is 2, here bond order is 3. More will be the bond order, more is the stability. So bond order directly proportional to stability, right? Why the stability increases when the bond order increases? When more number of bonds are there, the atoms come closer, then bond length will decrease, then it needs more energy. So bond order is more, stability is more, bond order is more, bond length is less. So bond order and bond length are inversely related. Bond order and stability. Bond order is more, stability is more. Bond order is more, bond length is less. Bond order is more, bond energy is more. Bond order is more, bond energy is more. That means here 2 bonds are there, here 3 bonds are there. Generally, which requires the more energy to break, double bond or a triple bond? Simply triple bond. That means more is the bond order, more will be the bond energy required. Understood? So this is the relation between the different parameters. Higher the bond order, higher will be the stability. Higher the bond order, less will be the bond length. Higher the bond order, less will be the more will be the bond energy. How can we calculate the bond order for a given molecule? According to molecular orbital theory, number of bonding electrons minus number of anti-bonding electrons by 2 is equal to bond order. Number of bonding electrons minus number of anti-bonding electrons by 2 is called bond order. What is bonding electron and what is anti-bonding electron? And that means student must have the knowledge on the molecular orbital theory. Even though I will explain what is bonding and anti-bonding molecular orbital. Right students? So bond order is equal to number of bonding electrons minus number of anti-bonding electrons by 2. This is the bond order. So these are the relations between the different parameters, right? Now you know the relation between the different parameters, and now we are going to discuss about the concept of molecular orbital theory briefly, and the terminology of HOMO, LUMO, and also bonding and non-bonding molecular orbitals. Look at this diagram. This is the molecular orbital energy diagram for O2 molecule. Molecular orbital energy diagram for O2 molecule. In this O2 molecule, oxygen atomic number is 8. Oxygen atomic number is 8. Right? O2 means 16 electrons are there. Atomic number of oxygen is 8, but O2 molecule has 2 oxygen atoms. Every oxygen contains 8 electrons, altogether 16 electrons are there. From the concept of the molecular orbital theory, this is the molecular orbital energy diagram for oxygen molecule. Molecular orbital energy diagram for oxygen molecule. Or you will look at in this direction, the total picture will appear, right? This is the molecular orbital energy diagram for oxygen molecule, right? This is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2px, pi 2py, pi 2px, pi star 2py, pi star 2px, sigma star 2pz. Z is taken as the internuclear axis. The orbitals which have the star mark can be considered as anti-bonding. The molecular orbitals with a star mark representing anti-bonding, they have more energy than the bonding. Among the sigma 1s and sigma star 1s, sigma 1s has less energy, sigma star 1s has more energy. Sigma 2s and sigma star 2s, sigma 2s has low energy and sigma star 2s has a higher energy. And similarly, this is the way of representation, and this is called molecular orbital energy diagram. Here energy is less as we are moving from sigma 1s to sigma star 2pz, the energy will increase. The energy will increase. Here and there I am representing the energies, right? Student here also must know what is called HOMO and LUMO. Students, in a given molecular orbital diagram, the molecular orbital which contains the electrons and possesses high energy called HOMO, and the empty orbital which do not contain any electron called LUMO. I will explain clearly by after filling the electrons. Here O2 is there. How many electrons are there? 16 electrons. Electron filling in the molecular orbitals also takes place according to the above principle. That is, first enters into the lower energy level and then enters into the higher energy levels. Total electrons 16. Here I am writing 2 electrons. So how many left? 2 more electrons left. 14 more left. Here I am writing 2 more. Then 12 electrons are left. Here I am writing 2 more. Here I am writing 2 more. Altogether 8 electrons. 8 electrons are filled in the different molecular orbitals. Now you have 8 more electrons because O2 molecule has 16. Next energy level is sigma 2pz. Here I am writing 2. So 6 more electrons are there. These two have the same energy. So you write 1 electron here, 1 electron here, and then 1 more electron here and 1 more. Altogether 14 electrons are filled in the different molecular orbitals. Now you have 2 electrons. Those 2 electrons are distributed here, right? This is called molecular orbital energy diagram filled with the electrons. From this diagram we are going to write its configuration, that is called MOEC. What is called MOEC? Molecular orbital electronic configuration. Write its configuration. Sigma 1s. Sigma 1s has 2 electrons. Then sigma star. Sigma star has 2 electrons. Sigma star 1s2 has 2 electrons. Then sigma 2s has 2 electrons. Sigma star 2s has 2 electrons. And then sigma 2pz. Sigma 2pz has 2 electrons. and pi 2py. Pi 2py has 2 electrons, pi 2px has 2 electrons, and pi star 2py has 1 electron, and pi star 2px has 1 electron. This is the molecular orbital electronic configuration for this diagram. So just simply I am representing this orbitals with electrons here, right? Look at this. In this sigma star 2pz is also there, but no electron at all. No electron at all. Here I am differentiating them. These have no star mark, all these have star mark. These can be considered as anti-bonding. These are considered as bonding, right? These are the anti-bonding molecular orbitals, these are the bonding molecular orbitals. Okay, it's all right. I am going to copy this electronic configuration in another paper. Look at this. Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2py2, pi 2px2, pi star 2py1, pi star 2px1, and sigma star 2pz0, right? This is the molecular orbital electronic configuration for the O2 molecule. Once again, you look at this diagram. In this diagram, this is the orbital having electron and possessing high energy. So these can be considered as HOMO. What is called HOMO? Among all the occupied molecular orbitals, these two possess high energy. So high energy occupied molecular orbital. Among all the occupied molecular orbitals, these two possess high energy. So this is called high energy occupied molecular orbital, simply called HOMO. And among all the molecular orbitals, this is the empty orbital. Among all the empty molecular orbitals, it has the lowest energy among the empty. That is why it is called lowest unoccupied molecular orbital. This is called LUMO, right? Here HOMO is pi star 2py, pi star 2px. LUMO is sigma star 2pz. Come to this one. What is the HOMO here? High energy occupied molecular orbital is pi star 2py1, pi star 2px1. LUMO means sigma star 2pz, right? 2pz0. Here both the HOMO and LUMO are anti-bonding, that you remember, right? Now we are going to explain molecule wise. Taking O2 molecule, first you have to find out the bond order. Number of bonding electrons minus number of anti-bonding electrons by 2. So bonding electrons, this is the bonding, 2 plus 2 plus 2 plus 2 plus 2, 10, minus anti-bonding, 2 plus 2 plus 1 plus 1, 8, 6 by 2, that is equal to 4 by 2. So its bond order is 2. And in this configuration it has 2 unpaired electrons. Look at this. So it is paramagnetic. Paramagnetic. This is about O2 molecule. Now we are entering into the another molecule. O2 minus. O2 minus means you are adding 1 electron to the O2 molecule. O2 molecule have how many electrons? 16. O2 minus means 17 electrons. So one new electron will be added. That new electron will be entered into here only, either this one or this one, because these two have the same energy. So that means the new added electron enters into the anti-bonding. So NB minus NAB by 2. NB means 10. Bonding electrons will not change, but one electron is added to anti-bonding, so it will become 7. So 2. Therefore 3 by 2. So bond order will be 1.5. It is paired, it is unpaired. One unpaired electron is there, so it is paramagnetic. Paramagnetic nature will not change, but the bond order changes. Here is 2, here is 1.5. When the bond order changes, when the bond order decreases, bond length increases. Next, we will take another example. O2 plus. O2 means how many electrons? 16. O2 plus means you have to remove one more electron. Then 15 electrons. 15 electrons means you remove one electron here and one electron here. Here is totally 10, 14 and 15. Only one electron is there. One electron. When compared with the O2, here is only one electron, here is no electron. So number of bonding electrons minus number of anti-bonding electrons by 2. Bonding electrons will not change, it will be 10. Anti-bonding electron, one electron is removed. So 6 will become 5. So that is equal to 5 by 2, that is equal to 2.5. But one unpaired electron is there, so it is again paramagnetic. Right? And go to the O2 plus 2 or O2 minus 2. O2 minus 2. O2 minus 2 means you will enter 2 more electrons to the O2 molecule. In O2 molecules 10 bonding and 6 anti-bonding. Now you are going to enter 2 more electrons. These 2 more electrons enters into the HOMO. HOMO has 1 electron. So you will add 2 more electrons, 2py2, 2px2. Understood? So NB minus NAB by 2. Bonding electrons are 10. Anti-bonding electrons, your added electrons enters into this anti-bonding, that's why it will become 8 by 2, that is equal 2 by 2, that is equal to 1. Here 2 electrons are entered, these 2 unpaired will become paired, so it is a diamagnetic. Then go for O2 plus 2. O2 plus 2. In O2 plus 2 means when compared with the O2 you have to remove 2 electrons. Electrons are removing from the HOMO. HOMO means you are removing electrons from here and here. That means there is no electron here, right? There is no electron here. But bonding electrons will be same, that is 10. Anti-bonding electrons only 4. So number of bonding electrons minus number of anti-bonding electrons by 2 is equal 10 minus 4 by 2, that is equal to 6 by 2, that is equal to 3. So no unpaired electrons, so it will become diamagnetic. Right? You will observe all these things carefully. O2, 10 bonding and 6 anti-bonding. O2 minus, 1 electron is added, that electron enters into the anti-bonding, that's why I am writing 7. O2 plus, I am removing 1 electron when compared with the O2, that electron is removed from the 6, so it will become 5. In O2 minus 2, when compared with O2, 2 electrons are added, those 2 electrons are added to the anti-bonding, so it will become 8. O2 plus 2, 2 electrons are removed, those 2 electrons are eliminated from the anti-bonding when compared with the O2 molecule, so the 6 will become 4, so 3. Now all the species have the bond order something. Now we are going to compare their bond length, magnetic behavior is clearly explained here. Then entering into the bond stability order, bond length order, bond energy order. Order of bond order. Order of bond order. First you write the bond orders. O2 2, O2 plus 2.5, O2 plus 2 3, O2 minus 1.5, O2 minus 2, it is 1. So order of bond order, which one has the highest bond order? O2 plus. So O2 plus greater than, then O2 plus 2, it is O2 plus 2 greater than, O2 plus greater than, O2 greater than, O2 minus greater than, O2 minus 2. This is the order of bond order. As per our previous discussion, if bond order is more, bond length less, then order of, this is the order of bond order. This is the order of bond order. Now order of bond length, reciprocal. So which one has the higher bond order, bond length? O2 minus 2. O2 minus 2 greater than, O2 minus greater than, O2 greater than, O2 plus greater than, O2 plus 2. So it has a higher bond length. If bond length is more, what about the bond energy? Order of bond energy. Order of bond energy. Length is more, easy to break. So bond energy will be less. So this has a higher bond energy. O2 plus 2 greater than, O2 plus greater than, O2 greater than, O2 minus greater than, O2 minus 2. This is the order of bond energy, bond energy. More is the bond energy, more will be the stability. So bond energy and stability order is this one. This is all about the explanation of different O2 molecules. Thank you for watching my videos. Students, please subscribe and share and like it my videos. Thank you for watching. And any suggestions or any requirements, please send your opinion through comment box. Thank you very much.